Dark matter. Have you ever wondered what exactly is the universe made of? According to the cosmological model, our universe was born 13.7 billion years ago, by a huge explosion that gave birth to our space like we know it nowadays, the Big Bang. Everything that exists was born in that immense explosion. Science development led us to more and more sophisticated and accurate technology to investigate the cosmos, and little by little astronomers and physicists have learned a lot about the universe, discovering stars, stardust, planets, satellites, asteroids, galaxies, nebulae, clusters of galaxies and so on, until recently we thought to be well advanced in the comprehension of matter distribution around the universe. Nevertheless, starting from the last century, observations suggest that there is far more to discover. As a matter of fact, all that exists in the universe seems to be much more than what we can detect. The mass we can see and measure is only a minimum fraction of the whole universe. Yes, because the larger amount of matter is invisible and undetectable by our instruments. It's like an immense halo that permeates the cosmos without emitting, absorbing and reflecting nor light neither electromagnetic wave. This is the dark side of the universe. This is dark matter. Now physicists assess that only the 15% of the matter in the universe is made of detectable ordinary mass. The overwhelming majority is made up of something that we can't detect directly, so scientists called it dark matter. The name dark is due to the fact that it doesn't shine, it doesn't absorb, it doesn't reflect light or any other electromagnetic radiation. We detect its presence by indirect effects only. It's like a phantom, we can't see it, it's completely invisible. Wait, what? How is that possible? Curious to know how? Stick with us and we will tell you how are things in this video. What is dark matter? Dark matter, a component of the universe whose presence is discerned from its gravitational attraction rather than its luminosity. Dark matter makes up 30.1% of the matter-energy composition of the universe. The rest is dark energy, 69.4%, and ordinary visible matter, 0.5%. Originally known as the missing mass, dark matter's existence was first inferred by Swiss-American astronomer Fritz Zwicky, who in 1933 discovered that the mass of all the stars in the Coma cluster of galaxies provided only about 1% of the mass needed to keep the galaxies from escaping the cluster's gravitational pull. The reality of this missing mass remained in question for decades, until the 1970s when American astronomers Vera Rubin and W. Kent Ford confirmed its existence by the observation of a similar phenomenon. The mass of the stars visible within a typical galaxy is only about 10% of that required to keep those stars orbiting the galaxy's center. In general, the speed with which stars orbit the center of their galaxy is independent of their separation from the center. Indeed, orbital velocity is either constant or increases slightly with distance rather than dropping off as expected. To account for this, the mass of the galaxy within the orbit of the stars must increase linearly with the distance of the stars from the galaxy's center. However, no light is seen from this inner mass, hence the name dark matter. Where can we find it? How can we know that it exists and how we measure it? Since the confirmation of dark matter's existence, a preponderance of dark matter in galaxies and clusters of galaxies has been discerned through the phenomenon of gravitational lensing, matter acting as a lens by bending space and distorting the passage of background light. The presence of this missing matter in the centers of galaxies and clusters of galaxies has also been inferred from the motion and heat of gas that gives rise to observed X-rays. For example, the Chandra X-ray Observatory has observed in the Bullet Cluster, which consists of two merging galaxy clusters, that the hot gas, ordinary visible matter, is slowed by the drag effect of one cluster passing through the other. The mass of the clusters, however, is not affected, indicating that most of the mass consists of dark matter. Matter is 30.6% of the universe's matter-energy composition. Only 0.5% is in the mass of stars and 0.03% of that matter is in the form of elements heavier than hydrogen. The rest is dark matter. two varieties of dark matter have been found to exist. The first variety is about 4.5% of the universe and is made of the familiar baryons, i.e., protons, neutrons, and atomic nuclei, which also make up the luminous stars and galaxies. Most of this baryonic dark matter is expected to exist in the form of gas in and between the galaxies. This baryonic, or ordinary, component of dark matter has been determined by measuring the abundance of elements heavier than hydrogen that were created in the first few minutes after the Big Bang occurred 13.8 billion years ago. The dark matter that comprises the other 26.1% of the universe's matter is in an unfamiliar, non-baryonic form. The rate at which galaxies and large structures composed of galaxies coalesced from density fluctuations in the early universe indicates that the non-baryonic dark matter is relatively cold, or non-relative acidic, meaning that the backbones of galaxies and clusters of galaxies are made of heavy, slow-moving particles. The absence of light from these particles also indicates that they are electromagnetically neutral. These properties give rise to the particle's common name, weakly interacting massive particles, WIMPs. The precise nature of these particles is not currently known, and they are not predicted by the standard model of particle physics. However, a number of possible extensions to the standard model such as supersymmetric theories predict hypothetical elementary particles such as axions or neutralinos that may be the undetected WIMPs. Extraordinary efforts are underway to detect and measure the properties of these unseen WIMPs, either by witnessing their impact in a laboratory detector or by observing their annihilations after they collide with each other. There's also some expectation that their presence and mass may be inferred from experiments at new particle accelerators such as the Large Hadron Collider. As an alternative to dark matter, modifications to gravity have been proposed to explain the apparent presence of missing matter. These modifications suggest that the attractive force exerted by ordinary matter may be enhanced in conditions that occur only on galactic scales. However, most of the proposals are unsatisfactory on theoretical grounds as they provide little or no explanation for the modification of gravity. These theories are also unable to explain the observations of dark matter physically separated from ordinary matter in the bullet cluster. This separation demonstrates that dark matter is a physical reality and is distinguishable from ordinary matter. How is dark matter and dark energy arranged in the universe? To answer these questions we need to step back, so let's rewind a bit the tape and go back in time. Story of dark matter, the first evidence in rotational velocities since the end of 19th to the beginning of 20th century. Many scientists were interested in so-called obscure stars and dark gases, little luminous matter that couldn't be identified with telescopes. In 1877, Italian priest Angelo Secchi, expert in stellar spectroscopy, in a paper, asked himself questions about the presence of scattered dark masses in space. In 1933, the Swiss physicist Fritz Zwicky was trying to understand the behavior of clusters of galaxies. In particular, while observing a cluster of 1,000 galaxies in the Coma Berenices, 150 million light-years far from here, he found some anomalies in their motion. In fact, they were rotating with a speed about 100 times faster than what the theory expected, as if the total mass of the cluster was about 400 times higher than it was. In other words, the gravity effect of the cluster was too low for such fast orbits. Therefore, Zwicky argued that there had to be much more gravity and more mass than what appeared to keep together these galaxies with those high rotational speeds. The Swiss was the first to use the term dark matter to express that lack of matter. If these observations were confirmed, we will get the surprising result that dark matter is present in larger amount than luminous matter, he said. Unfortunately, Zwicky wasn't very popular within astronomer community because of his short-tempered behavior. Therefore, at his time, his idea was considered absurd and set aside. 6 years later, the astronomer Horace Babcock observed other anomalies in the motion of stars in the Andromeda Galaxy. As a matter of fact, their rotation speeds, while proceeding towards the outskirts, didn't slow down, in contrast to gravitational theory. Nevertheless, process of measurement, because of technical limitation, it was essentially believed that the missing mass was made of faint stars, planets, meteor, scattered gas in interstellar spaces. Several decades passed and the thing came back to the surface thanks to the work in 1974 of some Princeton cosmologists who claim that there are good reasons to believe that the mass of galaxies had been underestimated by a factor 10 or more. The turning point occurred at the end of the 70s, when American astronomer Vera Rubin was working on the motion of spiral galaxies and assessed the same thing that Zwicky claimed 40 years before. Rubin and her colleague Ford had studied and measured the rotation curves of about 20 galaxies and had found that moving away from the center of mass, velocities didn't decrease. According to those data, galaxies couldn't stay in balance, they should have flaked off with the outer stars departing for the tangent. There had to be much more mass in there. To understand this concept and explain all these conclusions, we need to do a short digression about Newton's gravitational and Kepler's laws. Kepler's laws are deducted directly by Newton's gravitation. All rotational systems that can be modeled as a heavy central mass with some smaller and lighter objects orbiting around it can be investigated by applying Kepler's laws. The rotational speed only depends on the distance from the central mass and on the matter amount in the center, and do not depend on their masses. It is therefore expected that, proceeding towards the outskirts, the rotational speed decrease. If this doesn't occur, the obvious way to resolve this discrepancy is to conclude that the mass amount is higher and postulate the presence of non-luminous matter, dark matter, to balance the system. Scientific community was still skeptical about dark matter, so it was fundamental to find another method, using another independent data set, to compare results. Before we continue to look at dark matter, be sure to like or dislike the video so that we can continue to improve and make these videos better for you the viewer. Plus, be sure to subscribe to the channel clicking the bell so that you don't miss any of our weekly videos. Second evidence of dark matter. The gravitational lens effect. Nowadays we have another instrument to assess the amount of dark matter in the galaxies. According to Einstein's general relativity, if we interpose a mass between a distant electromagnetic source and an object that we're observing, since the mass curves space-time, this mass will act as a lens to bend the light from this source. The more massive an object, the more lensing is observed. By measuring the distortion geometry, the mass of the object can be deduced. If the gravitational lens mass is a galaxy, so we can get its mass by studying images with the gravitational lens effect. The mass of galaxies calculated with gravitational lens method is in reasonable agreement with galaxy rotation curves. The amount of dark matter assessed was 10 even 100 times the amount of ordinary matter. Therefore, the universe appeared made up of dark matter with some little amounts of ordinary matter. This was the outstanding conclusions that originally led scientists to deny its presence. Today we also know that the distribution of dark matter is quite bizarre. It isn't uniform as well. What most intrigues is the halo arrangement around galaxies. If we move from the center towards the outskirts, ordinary matter decreases whereas dark matter increases. The same goes to clusters of galaxies. For example, in the Milky Way, the amount of ordinary and dark matter are comparable. By contrast, outside dark becomes dominant. Universe is like made up of bubbles of dark matter in which galaxies swim like ducklings. Third evidence of the presence of dark matter. The cosmic background radiation, CMB. According to cosmology, we all know that the universe is born 13.7 billion years ago from a huge explosion, the Big Bang. Nowadays, we have detected a landmark evidence of the Big Bang origin of the universe. It's about the cosmic background radiation, CMB. This was discovered for the first time in 1964 by physicists Arno Penzias and Robert Wilson during radio astronomy and satellite communication experiments. This is an electromagnetic radiation permeating uniformly the universe, as a remnant from an early stage of the universe. It is the oldest electromagnetic radiation in the universe. That's why it's an important source of data. According to COBE satellite, sent into orbit from 1988 to 1993 to measure CMB, cosmic background radiation around the universe, cosmic background radiation is not constant throughout the universe, but fluctuates slightly. In fact, there are colder and warmer areas. These differences are called anisotropies. But why are we talking about CMB, cosmic background radiation? How does CMB, cosmic background radiation, is related with dark matter? It's easy to say. According to the analysis of this radiation, it was possible to have a precise reconstruction of the mass composition of the universe. In fact, if we draw a graph of the fluctuation of cosmic radiation, this provides us a data set on dark matter. From the curve we obtain, in fact, we deduce that the mass of the universe cannot be made of ordinary matter only, otherwise we would find a different graph. The result of the fluctuation of the background radiation tells us that there is a huge amount of matter that doesn't interact with electromagnetic rays, and therefore we can neither see nor detect it directly. According to the numbers, after gravitational lens effects and the spiral galaxy's rotational curves, also this alternative approach shows that dark matter represents about the 80% of the total mass of the universe. What is dark matter indeed? What is it made of? Over the course of time, many hypotheses have been formulated. At first, this missing mass was thought to belong to invisible stars and gases that could, however, emit radiation. As a matter of fact, there is a lot of mass of this type around the universe, but its amount is far lower than the missing mass and is not enough to explain dark matter. Then the focus was on macho, massive, compact, halo, objects, particles, non-emitting heavy objects like black holes, neutron stars, white and brown dwarfs. After years of observations, astronomers assessed their effective presence, but their total mass, deducted using their gravitational lens effects, is lower again, because would represent 15% at most, of what we would expect as dark matter. All these failure led to the formulation of non-ordinary matter theories to justify dark matter. The most popular is WIMP, weakly interactive massive particles theory. WIMP particle are massive particle that would interact very weakly. According to the theory, WIMP, weakly interactive massive particles, have still been found in the early stages of formation of the universe, would interact with ordinary mass, annihilating, maintaining a kind of balance. At a certain moment, however, because of the rapid expansion of space, these interactions would stop, and by that time, dark matter particles has remained unchanged until today to detect WIMP, weakly interactive massive particles. If they exist, we have different ways. We can try to reveal them in our particles accelerators like LHC, Large Hadron Collider, of CERN in Switzerland, hoping to observe the energy released when dark matter, in particular conditions, interacts with ordinary matter. Alternatively, we can build ad hoc detectors, sheltered from energy interferences and cosmic particles, like the Xenon 1-ton experiment at the Gran Sasso Laboratory in Italy or the Super Kamiokan detector in Japan. Eventually, we can always hope to detect some WIMPs, weakly interactive massive particles, interaction events with ordinary matter, directly in the cosmos, by means of our radio telescopes. So far, it should be noted that no WIMP, weakly interactive massive particles, has been detected by any of these huge experiments. Conclusions. Physicists now believe that dark matter is approximately the 85% of the whole mass in the universe and represents about a quarter of its total mass, energy density. These proportions are quite outstanding and flip our point of view on the universe. Matter, as we all know it, represents a negligible and almost ridiculous quantity of the whole mass in the universe. On the one hand, more and more exciting discoveries are yet to come, but on the other hand, it's so shocking and upsetting that all we can see is just amidst an immensity that we still cannot understand. You can say everything about dark matter, except that it goes unnoticed. This video ends here. Thanks for watching. Everyone, did you find dark matter exciting? Is there something more you want to know about dark matter and its relationship with the universe as we know it today? Let me know in the comments below. Thank you so much for watching our video completely till here. Stay connected with quantumphile family for more such interesting video, and don't forget to like, subscribe and share this video. Right now we are in growing phase, so every subscription and like will motivate us a lot to make more such a video. Thank you, have a great day. Stay safe and enjoy a life. See ya next time.